Hello everybody, I'm Rahul U K, bearing USN 1BI20CS133, and I'm doing presentation on A-stable multivibrator using IC555 timer. So before that, let us discuss what is multivibrator. Multivibrator are categorized by two amplifying devices like electron tubes, transistor, and other devices like capacitor and cross-coupled by resistor. So multivibrator are categorized by two amplifying devices like electron tubes, transistor, and other devices like capacitor and cross-coupled by resistor. A multivibrator is one type of an electronic device that is used to implement a two-state systems like flip-flop, timers, and oscillators. Multivibrator is categorized by two amplifying devices like electron tubes, transistors, and other devices like capacitor and cross-coupled by resistance. A multivibrator is one type of electronic devices that is used to implement a two-state system like flip-flops, timers, and oscillators. Next, if we come of types of multivibrator. So multivibrator are classified into three types based on the circuit operation, namely astable multivibrator, bistable multivibrator, monostable multivibrator. So before that, let us discuss what is astable multivibrator. Astable multivibrator is not stable and it is repeatedly switches from one state to another. So astable multivibrator is not stable and it repeatedly switches from one state to another. In case of bistable multivibrator, the bistable multivibrator circuit is stable that can be changed from one stable to other stable state by an external trigger pulse. So in bistable multivibrator, we require an external trigger pulse to change from one state to another state. This multivibrator circuit is also called flip-flop, which can be used to store one bit of data. So this multivibrator circuit is also called as flip-flop, which can be used to store one bit of data. This is about bistable multivibrator. If we go for monostable multivibrator, we can see that in monostable multivibrator, one state is stable and remaining state is unstable. So in monostable multivibrator, one state is stable and remaining state is unstable. A trigger pulse is the route to the circuit to enter the unstable state. A trigger pulse is the route to the circuit to enter the unstable state. When the circuit enters into the unstable state, then it will return to normal state after a fixed time. In case of multivibrator, in the two monostable multivibrator, one state is stable and remaining state is unstable. A trigger pulse is always required to enter to unstable state. After when the circuit enters into the unstable state, then it will return to normal state after a fixed time. So this is about the three types of multivibrator: astable multivibrator, bistable multivibrator, monostable multivibrator. Astable multivibrator means it multivibrator which is not stable and repeatedly switches from one state to another. In case of bistable multivibrator, it can change the state from one to another state by an external trigger pulse. In case of monostable multivibrator, one state is stable and another state is unstable. In this case, the trigger pulse is required. Next, if we go for astable multivibrator working. In case of astable multivibrator working, this type of multivibrator includes two amplifying stages that are connected to with a respective capacitive resistive coupling networks in a positive feedback. So in case of multivibrator, it includes two amplifying stages that are connected with the two capacitive resistive coupling networks in a positive feedback. The amplifying elements are FETs, JFTs, op amps, vacuum tubes, etc. So the amplifying elements are FETs, JFTs, op amps, vacuum tubes, etc. The A-stable multivibrator circuit using BJTs, which is also known as bipolar junction transistor, is drawn in the form of cross-coupled pair. The output terminals of the vibrator can be defined as the active devices that will have opposite states. One will have low stage, whereas other will have high voltage. So a stable multivibrator circuit using BJTs is drawn in the form of cross-coupled pair. The output terminals of the vibrator can be defined as the active devices that will have opposite sides. One will have low voltage, whereas another will have high voltage. The stable multivibrator circuit has two unstable states that change alternatively with the max transition rate due to accelerating positive feedback. So in this important working is it run due to the accelerating positive feedback. A stable multivibrator circuit has two unstable states that changes alternatively with the max transition rate due to accelerating positive feedback. It is employed by the coupling capacitors that suddenly transfer voltage variation because the voltage across the resistor cannot change quickly. So this happens because the voltage cannot change quickly, hence the transfer voltage varies. In every state, one transistor is turned on and remaining one is turned off. In every state, one transistor is turned on and the remaining is turned off. So one fully charged capacitor discharges slowly, therefore changing the time into an exponentially alternating voltage. So one fully charged capacitor discharges slowly, therefore changing the time into an exponentially altering voltage. So here we can see the diagram of an astable multivibrator. Here you can connected R1, R2, R3, R4 as a resistor, and C1, C2 are the capacitor, and this one Q1 and Q2 are the transistor, and V are the voltages. So here we can see that a stable multivibrator circuit has two unstable states that changes alternative with max transition rate because due to a positive feedback. It is simply due to the coupling resistance that certainly transfer voltage variations because the voltage across the capacitor cannot change quickly. In every state, one transistor is turned on and remaining one is turned off. So one fully charged capacitor discharges slowly, therefore changing the time into an exponentially altering voltage. So if we see from again, this type of multivibrator includes two types of amplifying devices that are connected with the two capacitive resistive coupling networks in a positive feedback. The amplifying elements are FPGAs, JFTs, op-amps, vacuum tubes, etc. The A-stable multivibrator circuit is using BJTs is drawn in the form of cross-coupled pair. The output terminal of the multivibrator can be defined as the active devices that will have opposite states. One will have low voltage, whereas other will have high voltage. So we have seen this already. Again, we will see that R1, R2, R3 resistor, C1, C2 are the capacitor, and these two are the transistors. Next, at the same time, remaining empty capacitor charges quickly. The operation of the above circuit is based on the forward bias junction on the turn of the turned on BJT that can provide a route for restoration of the capacitor. So this is worked on the forward bias condition. Next, if we use A-stable multivibrator using 555 timer. So A-stable multivibrator using 555 timer. The designing and the working of A-stable multivibrator using 555 timer is done by using transistor and operational amplifier. Basically, the stable multivibrator is done by using transistor and operational amplifiers. The 555 IC timer affords exact time delay from millisecond to hours. The 555 IC timer affords exact time delay from millisecond to hours. The oscillation frequency can be measured manually by small modification. The oscillation frequency can be measured manually by small modification. The 555 timer IC is relatively cheap, stable, and user-friendly integrated circuit. Then that is apt for circuit designers with both A-stable and monostable applications. So why we require this A-stable multivibrator? Because it's of relatively cheap, stable, and user-friendly integrated circuit. So many designers use apt for this circuit. Next, the first 555 integrated circuit was designed in the year 1971 by the Corporation of Singles as SC555 or NE555. As you all know, the first 555 integrated circuit was designed in the year 1971 by the Corporation of Singles as the SC555 or the NE555. The A-stable multivibrator using 555 AC is a simple oscillator circuit that generates continuous pulses. As you know, a simple oscillator circuit, it generates always a continuous pulses. The frequency of the circuit can be controlled by shifting the values of R1 and R2 and capacitor C1. Okay, this is basically is a circuit of a 555 IC timer. As you can see, there is R1, R2, C, where we can change the frequency which is controlled by R1, R2, R3, R1, R2 and capacitor. Next, if we come to design of A-stable multivibrator, how we design basically the design of A-stable multivibrator. Designing steps of A-stable multivibrator given below. As you can see, the required components are NE555 or SC555 resistors, which are of 1 mega ohm, which is of 2, which we require two resistors and 1 kilo ohm resistor. Capacitors are of 0.01 microfarad and 1 microfarad and LED. The capacitor in the above circuit charges through the two resistors R1 and R2, and their charging time can be calculated using T charges is equal to 0.69 into R1 plus R2 into C1. During this charging time, the output is high at that is 1.838 seconds. So as we can see, this is the formula to calculate the T charges. It is 0.69 R1 plus R2 into C1. During the charging time, the output is high. That is, we can see the timing is 1.38 seconds. The capacitor discharges to the resistor R2, and then the discharging time can be written as we can see, it is the charging time, just discharging time. Discharging time is equal to 0.69 R2 C1. So here it is R1 plus R2 C1, and here it is R2 C1. During this discharging time, the output is low, that is 0.69 second. In the charging case, the output is high, that is 1.38 second. In case of discharging time, output is low, that is 0.69 second. So the total time period T is equal to T charge plus T discharge. As you can know, the total time is equal to T charge plus T discharge, which is equal to 1.38 plus 0.969, which is equal to 2.07 second. So the total time period is equal to 2.07 seconds. If we convert into frequency, that is the oscillation frequency is 0.483 hertz. So 0.483 hertz. The duty cycle can be calculated in the following manner. As you can see, we know the time charge, and the time discharge, and the frequency. From this, we can calculate the duty cycle. But for duty cycle, we require only single formula: T on by T on plus off. We can see T on by T on plus off. That is 1.38 by total time 2.07. That will give 66%. So duty cycle of this value is 66%. Next, if we come for working of a stable multivibrator. When the power is turned on, consider the flip-flop is clearly cleared initially. Then the output of inverter will be high. As you know, when the power is turned on, the flip-flop is cleared initially. Then the output of the inverter will be high. The charging of the capacitor will be done by using two resistors R1 and R2. We know that the charging of the capacitor will be done using two resistors R1 and R2. When the voltage of the capacitor goes above 2 by 3rd VCC, then output of the higher comparator will be high. It changes the control flip-flop. When the voltage of the capacitor goes about 2/3 of the VCC, then the output of the higher comparator will be high. It changes the control flip-flop. So the control flip-flop Q output will be low and Q dash will be high. As you know, if that changes, Q will be low and Q dash will be high. So the final output of the inverters will be low. At the same time, the Q1 transistor switches on and the C1 capacitor starts discharging through resistor R2. As you can see in this diagram, this is based on this diagram. That is Q will be low, Q dash will be high. So the final output of the inverters will be low. At the same time, Q1 transistor switches on, and the Q2 transistors and C1 capacitors starts discharging through resistor R2. So this is basically internal circuit of the 555 timer is stable, and this is the graph. Here you can see the VCC, that is high, low, high, low. In this case, till 1/3 the capacitor charges and again discharges through RB. Till R1 plus RA plus RB it charges, and in through RB it decreases. Like it decreases by 1/3 of the VCC and it increases by 2/3 of the VCC. So this is basically the capacitor and the output voltage waveforms. When voltage of the capacitor is less than 1 by 3rd VCC, the output of the lower comparator will be high. When control flip-flop gets it set to 1, then the voltage of the capacitor is 1/3 of the VCC, then the output of the lower comparator will be high, and the control flip-flop gets to set to 1. When the discharge transistor Q1 gets off, the capacitor gets charged and continuously this process occurs. According to the status of the output, the LED at the output will blink. So based on this, that the when the voltage capacitor is one less than 1/3 VCC, then the output of the lower comparator will be high. Then the control flip-flop gets to set to 1. Then the discharge transistor Q1 gets off, then the capacitor gets charged and continues as this process. According to the status of the output, the LED output will be blink. When the low voltage is applied at the fourth pin, that is reset pin of the IC, then it resets the IC. So when the voltage applied at the fourth pin, that is reset pin of the IC, then it resets the IC. When the low signal is applied to the base of the Q2 transistor, then it switches on by the capacitor. When the low signal is applied to the base of the Q2 transistor, that is another transistor. Then it switches on the capacitor by the transistor. Now, if we come for advantages and disadvantages of a stable multivibrator. So this multivibrator changes between one stable state to another stable state continuously. This permits multivibrator to power themselves and achieve work at a constant rate without impact from any external forces or actions. So this permits multivibrator to power themselves and achieve work at a constant rate without impact from any external forces or action. So why we more advantage of this multivibrator or the two age stable means it changes from one state to another state continuously, which permits themselves to power themselves and achieve work at a constant rate without impact from any external force or action. Also, this now multivibrator are low cost to produce and simple to design. In this case of multivibrator, it is of low cost to produce and simple to design. This multivibrator do not transfer the whole output signal to the input. This multivibrator do not transfer the whole output signal to the input. This is due to the resistance in the circuit, the non-existence of totally closed loop at the output terminals, and leaning of one transistor or the capacitor to the absorb energy at somewhat different rate than a other. So this multivibrator changes between the one stable to another state continuously. This permits multivibrator to power themselves and achieve work at a constant rate without impact from any external forces or action. Also, these vibrators are low cost to produce and simple to design. This multivibrator do not transfer the whole output signal to the input. This is due to the resistance in the circuit, non-existence of a totally closed loop at the output terminals, and the leaning of one transistor capacitor to absorb energy at somewhat different rate than the other. Next, if we come to the application of A-stable multivibrator, where we can use this A-stable multivibrator. The application of A-stable multivibrator involved in radio gauge to transmit and receive radio signal. So the main application of the A-stable multivibrator involved with radio gauge to transmit and receive radio signal, which is very important. Also, we used in time or the Morse code generators and some systems which require a square wave like analog integrated circuit and TV broadcasts. So also it is used in the time Morse code generators and some systems which require square wave like analog integrated circuits and TV broadcast. For integrated and TV broadcast we require a square wave. They are used in pulse position modulation. They are used in pulse position modulation, frequency modulation, etc. As they are simple, reliable, and easy to construct. So here is the main thing. So main thing is that it's very simple, reliable, and easy to construct. Hence, they are used in the pulse position modulation, frequency modulation, and etc. It is used in construction of voltmeter and SMPS. So it is used in the construction of voltmeter and SMPS as a timing oscillator or the clock of the computer system. So it is used as a timing oscillator or a clock of a computer system. It is also used in flashing lights, switching and power supply circuits. It is also used in switching light switching and power supply circuits. Next, frequency shift keying. If we go for frequency shift keying, in A-stable multivibrator, the output changes accordingly to the charging and discharging to the capacitor, which is a trigger pin. In A-stable multivibrator, the output changes according to the charging and discharging of the capacitor, which is at the trigger pin. Initially, consider that the flip-flop is set. In a A-stable multivibrator, the output changes accordingly to the charging and the discharging of the capacitor, which is at a trigger pin. Initially, consider that flip-flop is set. Therefore, Q dash will be 0. This turns off the transistor Q1 and the output of the timer is high. Since Q1 is off, the capacitor C starts charging up towards plus VCC through resistor RA and RB. As we know, therefore Q dash will be 0, which turns off the transistor Q1 and the output of the transistor is, that is timer is high. So when Q dash is equal to 0, it turns off the transistor Q1, the output of the timer is high. Since Q1 is off, capacitor C starts charging up towards plus VCC through a resistance RA and RB. Capacitor is connected to a threshold terminal and reference voltage of the comparator 1 is two-thirds of the VCC. When voltage is equal to or greater than two-thirds of the VCC, the output of comparator 1 goes high. This turns on transistor Q1 and output timer goes low. Now this happens exactly reverse. That is capacitor connected to the threshold terminal and reference voltage of the comparator is two-thirds of the VCC. When the voltage is equal to or greater than two-thirds of the VCC, the output of the comparator 1 goes high. So in this case it will go slow, in this case it will go high, which turns the transistor Q1 and output timer of the goes low. In this case the transistor Q1 and the output timer is high, in this case it will go low. Next, basically this is the diagram of the shifting, that is frequency shift keying. This is diagram of frequency shift keying. As you can see, these are the op-amps used here, and this is a flip-flop, the ISR flip-flop used here. Then this is the resistor R1, R2, R3, and this is RA, RB resistor. And this is RA resistor. As you can see, there is a process of discharging and charging, and we require a NOT gate for the construction of it, and we require a VCC and a reset. So this is basically an internal diagram of this, and this is an external diagram. As you can see, this is a 555 timer rated. So the pin diagram, as you can see, this is 10 kilo ohm, R4, R1 is 50 kilo ohm, R2 is 47 kilo ohm, R3 is 50 kilo ohm, and we use the C1 C2 capacitor, which is of 10 nanofarad. Next, now the capacitor C discharges through transistor Q1 and the resistor RB when capacitor falls below one-third of the VCC, which is the reference. As you see in this diagram, based on this we are concluding that the capacitor C discharges through transistor Q1 and resistor RB when capacitor falls below one-third VCC, which is reference. Voltage of the comparator to the output of the comparators go high and flip-flop sets. So when the voltage of the comparator to the voltage of the comparator goes high and the flip-flop sets. Hence Q dash is equal to 0, and again transistor Q1 turns off and the output of the timer is high, and it turns off and the output of the timer is high. Again process is limited in this case when the capacitor C discharges through capacitor transistor, when capacitor C discharges transistor Q1 and the resistor RB, when capacitor falls below 1/3 VCC, which is a reference voltage of the capacitor 2, that the output of the capacitor goes high and the flip-flop sets. Hence Q dash is equal to 0. Again the transistor Q1 turns off and output of the timer is high. Again the process is repeated. The capacitor of the charging time Tc is equal to, in this again if we can see the formula, that is charging time 0.69 Ra plus Rb into C. In case of discharging time, it is 0.69 Rb into C. It's same in case of the stable multivibrator. In case of total time period, we calculate the both. T is equal to 0.69 Ra plus 2 Rb into C. Now, in the total time period, the formula changes. That is 0.69 Ra plus 2 Rb into Rc. Frequency we can calculate like 1 by of it. That is 1.45 by Ra plus 2 RB into C. So this is basically the frequency shift keying application, major application. So in stable multivibrator, the output changes according to the charging and discharging of the capacitor, which is a trigger pin. Initially consider that the flip-flop is set. Therefore, Q dash is equal to 0. This turns of the transistor Q1 and the output of the timer is high. Since the Q1 is low, capacitor C starts charging up towards plus VCC through resistor RA and RB. The capacitor is connected to the threshold terminal and the reference voltage of the comparator 1 is 2/3 of the VCC. As we can see, when voltage is equal to greater than 2/3 of VCC, the output of the comparator goes high. This turns on the transistor Q1 and the output of the timer go low. So this is basically internal diagram of it, and this is external diagram of it. It is a 555 timer rated. Next, as we can already read this, that the capacitor C discharges through transistor Q1 and the resistor RB when its capacitor falls below 1/3 of the VCC, which is a reference voltage of the comparator to the voltage of the comparator goes high and flip-flop sets. Hence, Q dash is equal to 0. Again, the transistor Q1 turns off, the output timer is high. Again, the process is repeated. In this case, the capacitor charging time Tc, which is given by 0.69 Ra plus Rb into C. Capacitor discharging time at TD is equal to 0.69 Rb by Rb into C. Total time period of the waveform T is equal to 0.69 Ra plus 2 into Rb into C. Frequency, that is F is equal to 1.45 by Ra plus 2 into Rb into C. So this is basically the presentation on A-stable multivibrator using 555 IC timer. Thank you.